So, in this module we will get started with the basics of Hilbert space and then get on to the reproducing kernel Hilbert space. This is followed by the proof of the representer theorem, which has important consequences. Okay. So, let us start with an orthonormal basis and then endow it with the completeness property, and this leads us to the notion of Hilbert space. We start with orthonormal basis and we endow it with the inner product definition, and which is complete, and I will bring in these details very carefully, and that leads us to the Hilbert space, and from the Hilbert space over the kernels we will define what is called the reproducing kernel Hilbert space. Okay. Let xk k equals 1 to infinity be an orthonormal basis for an inner product space which is given by F, and this space could be possibly of infinite dimensions. It could be an infinite dimensional space. So, when we talk about inner product space, that means this inner product is defined in this on this vector space, right. You start with a vector space for which you have an orthonormal basis, and when we endow this vector space with this notion of inner product definition, then we are dealing with an inner product space. So, we all know what inner products are, I mean at this stage, because we have dealt with it in the past, but put formally I give you two vectors xj and xk. The inner product is defined by this notation, which is given by xj transposed xk, and since vectors xk k equals 1 to infinity they form an orthonormal basis, this inner product is 1 when j equals k and 0 otherwise, right, and the 1 ensures their norm, the norm condition, the norm is 1 and it ensures that it is an orthonormal basis. Okay. Let H be the largest and most inclusive space for these vectors. So, for some vectors, so let H be the largest and most inclusive space of vectors for which the set xk k equals 1 to infinity is a basis. So, then any vector x not necessarily lying in this space script f, because script f is an inner product space and it is endowed with this orthonormal basis, right, and any vector x that belongs to this space H, which is the most inclusive space which does not include f, can be written as a linear combination of these orthonormal bases. Right, this vector x can be written as x equals summation k equals 1 to infinity ak times xk, that is a linear combination of the orthonormal bases. And why this is a subtle issue, right, not necessarily lying in this space F, because in limit form, limit as n goes to infinity xn need not belong to this space F, right. I can have a limit of this vector or a limiting vector, and the limiting vector need not be part of this space. That is the reason why we want to bring in this notion of another space which is larger than this space F, which is inclusive of this condition. So, this is a subtle issue, and we will discuss this property as we go through the rest of the details within this module. Yeah. So, I think the most important detail here is this is a converging vector, right. The limit of this vector is a converging vector, and the converging vector does not belong to this space, and that is what I mean. So, x star is this converging vector, and this converging vector does not belong to this inner product space. And to endow this inner product space with the completeness property, that is, I want to bring in this sense of converging vector to be also part of another space. I bring this this largest and most inclusive space, which is H, which accommodates the subtle condition. Okay, we will get into these details slightly later. So, one subtle thing that you might see here is just from a notational standpoint of view. If you just focus on this equation here, this is saying that any vector can be written as can be represented using these bases xk, but I use this xn here, and this n is basically a sequence of such vectors. So, if this really confuses you, you can bring in this n in the superscript, which is indicating that you have a sequence of vectors, and we are looking at the convergent vector which is x star, which is a limit as n goes to infinity of this vector xn, and that may not be belonging to this inner product space script f. Okay. So, this is a small detail. So, do not confuse yourself with the index of the basis in this infinite dimensional space. Now, what we do is we define a new vector yn, which is equal to summation k equals 1 to n ak xk. That is, I am looking at a linear combination of some n vectors. So, similarly, I define ym to be the linear combination of m such vectors k equals 1 to m. Now, for n greater than m, I compute this norm square of the difference vector yn minus ym. So, this is expanded as summation k equals one to n akxk minus summation k equals 1 to m akxk squared, which is nothing but within the norm summation k equals m plus 1 to n akxk squared. Okay. Now what I can do is I have to replace this with an inequality, and this is I pull the norm inside, right. So therefore I can say this is equal to summation this is norm of a summation of something is less than or equal to summation of the norm something, right. So this is basically summation k equals m plus 1 to n ak square times norm xk square, right. This is sort of a straightforward inequality, and this can be simplified if you assume that the norm is 1, because that is where we started off. They are orthonormal basis. So this is nothing but summation k equals m plus 1 to n ak square, right. This is norm 1. So this partial sum from k plus from k equals m plus 1 to n has some interesting consequences. That is, in the limit when m and n tend to infinity, this sum should dive to 0, right. So let us list these properties here. Summation k equals m plus 1 to n, this partial sum ak square heads to 0 as m comma n tend to infinity, that is this converges to 0, and summation k equals 1 to n ak square is finite. I mean, in the square sum it is basically finite. So what we want from this is we want to lead to the notion of what a Cauchy sequence is, and that is the reason why we are bringing this this picture through a series summation. We pick an epsilon greater than 0 and m to be significantly large, such that summation k equals m plus 1 to infinity ak square is less than some tolerance epsilon. Now since summation k equals 1 to infinity can be of this quantity ak square can be broken down into two sums, k equals 1 to m ak square plus summation k equals m plus 1 to infinity ak square summation from k equals 1 to infinity ak square is less than infinity, is finite. So what we have done is the following: we pick m to be very large such that this summation k equals m plus 1 to infinity, that is across the tails, I have a sequence like this. So m is possibly here, and summation from m plus 1 to infinity is this region which is over these coefficients ak square. This is less than epsilon, and we assume that the series sum, a summation which is summation k equals 1 to n ak square is finite. So this quantity on the right hand side of equation 1, first term in the right hand side of equation 1 is finite, the second term is bounded by epsilon. So therefore the infinite series sum is bounded, or it is finite. So with this we have this notion of so with this intuition, what we have with the series summation, we can think about it in the framework of a sequence of vectors in a normed space, where the norm of the difference vector is within epsilon, and then with this notion we can define what a Cauchy sequence is in terms of convergence properties. Okay. So a sequence of vectors in a norm space. So when I mean norm space, that means it is a vector space endowed with a norm. A norm is a quantity which is non-negative. So when you take the norm of a vector, right, you can have different norms, L1 norm, L2 norm, so on and so forth. So these details I have dealt with in the earlier course in NPTEL that I have offered, which is mathematical methods and techniques in signal processing. So you can define various norms. You have L1 norm, L2 norm, L infinity norm, sup norm, etc. Okay. So depending upon your definition of the norm, so norm basically is a quantity which is non-negative because it has some notion of distance, right. So norm of a vector can be 0 if the vector is 0, and for anything other than that it is positive. Okay. For example, in the L2 sense, norm of x, which is written like this, can be written as square root of x1 square plus x2 square dot 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 plus xn square, where x1, x2, x3 so on are the coordinates of the vector x, right. Vector x is basically x1 dot 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 till xn. So when I talk about normed space, I mean that a vector space that is endowed with a norm. Okay. So let us erase these details so that we do not clutter the slide. So a sequence of vectors in a normed space for which the Euclidean distance norm yn minus ym is less than epsilon for any epsilon greater than 0 and integers m comma n that are greater than some value capital M is a convergent sequence called the Cauchy sequence This also means that the sequence yn n equals 1 to infinity is Cauchy if the norm yn minus ym tends to 0 as m comma n heads to infinity. Now, this is where we are arriving at into convergent sequence, like the way you think about a set of numbers, that a sequence that converges. You can think about a set of scalars that converge. You can also think about a sequence of vectors that converge. It can be a converging vector, it can be a convergence based upon some property of the vector, which in this case is the norm, which is the Euclidean distance, right. And what we want is this convergent vector may not be part of the original inner product space, and that is the reason why we are bringing the subtlety here. And we want to accommodate the convergent sequence also to be part of a bigger space, and that is our Hilbert space H. So, I did not talk about what a Hilbert space is, so I will be more clear here. So, the space script H is the Hilbert space or inner product space. This is more complete than F. F is our inner product space and H is the script H is the Hilbert space. H is more complete than F because of two things. Every Cauchy sequence of vectors taken from this space converges to a limit in this space. And most important of all, H inherits the inner product space properties. So, if you think about the hierarchy, you have the vector space. From the vector space you endow it with a norm that becomes a normed vector space, and with this norm you endow it with an inner product notion, and that is an inner product space, and you consider a sequence of vectors in the inner product space. They have to be convergent, and a Cauchy sequence of vectors taken from this space should converge to a limit which also belongs to that space, and that is this Hilbert space, which I would say is a complete space. Now, there is a subtle issue which I will pinpoint. The question is, are all Cauchy sequences convergent. The answer is no. For example, if you look at this series summation, which we are all familiar, summation 1 upon k factorial, where k is greater than or equal to 0 over all k, and let us say the space is over all rational numbers. Let us say we have a space of all rational numbers and that space is Q, and I consider this series summation 1 upon k factorial for k greater than or equal to 0, and I know this series sum heads to E when when I take large k going to infinity, and this is a transcendental number which does not belong to the space of rationals. So, my Cauchy sequence, a sequence is Cauchy if you take the difference of you take the norm of the difference vector, and as m comma n tends to infinity, this was our definition for the Cauchy sequence, that it is within epsilon tolerance, that means it converges. This is our notion of convergence of a sequence in terms of the Cauchy sense. But the convergent value or the converging value, that may not be part of the original space. So, this is a clear example where all Cauchy sequences or Cauchy sequence need not be convergent, but if it is a convergent sequence it is Cauchy, but if it is a Cauchy sequence it is not convergent. This is very important. All convergent sequences are Cauchy, but all Cauchy sequences are not convergent. I mean, this is a very important detail, right, because when we talk about completeness it has to be defined over a certain space, and for which we have to bring in these details, right. But this picture should be very clear to you how we go from a vector space to a Hilbert space, and a Hilbert space is a more is a vast space because it is it endows completeness to an inner product space. So, now we have a much richer space of vectors or functions or whatever we may call within this space that we can play with. Okay. And this is very important, particularly when you think about expansion of signals, like the way we thought about expansion of functions using an orthonormal basis. We can think about expansion of functions using this orthonormal basis, and then what can we say about the convergence of that sequence when we expand in terms of the basis. Does the sequence lie within the space, and these are the subtle issues of convergence that we have to discuss in this module, so that it is clear when we bring in these details. Okay. So, with this we will end this module, and we will work further.